Okay, so we started looking at our instruction set last time, right? For the leg V8, whatever version of ARM, subset of ARM. All right, we were starting to look through a big list of these guys down here. I had you read through a couple of things, right? Where's my list of stuff? Okay, so as a reminder from last time, we talked about that there's 32 general purpose registers in ARM. 31 of them are truly general purpose. The other one is a zero constant. Then we have 2 to the 62nd on-chip memory hold things. And we'll see, we kind of talked a little bit how that relates when we looked at our load this last time, which gave an offset. We'll review that here in a minute. All right, so we looked at all the arithmetic things here. What's an immediate value? What's the difference between add immediate and the normal add? Go ahead.
It's a constant value.
Okay, so add immediate allows us to have a single constant value being part of the arithmetic. So there's a subtract immediate as well. So we can't use two constants. We can just use one. So in this example, there's the literal 20 being added to x2, storing the result inside of x1, or this guy here. Okay. What are flags used for? Somebody else. So like this example here, add and set flags. What's the purpose of the flags? I would have made a good quiz question, Maddie. The flag one. Well, no, it might look the same to you there, but we talked about what the flags meant last time. Go ahead.
It can help you determine if there's something wrong with the program. Like, you know, set a flag and say you go over size.
Okay, not necessarily something wrong, but yeah, but in some ways, if something potentially unexpected happens. So, for instance, there's an overflow flag that might get set if you add two numbers and you're putting them into as an example, into an 8-bit register. And those two numbers add up to something greater than 255, which is the largest unsigned value you can store in an 8-bit register, right? Then it's gonna put the bits in there that it can fit, but then it's gonna have a flag that says there was an overflow in the last arithmetic. Just FYI, you might not be able to trust the value that's in your destination register. That makes sense? Why is it that the maximum value we can fit in an 8-bit register is 255? The maximum unsigned value. Somebody else. Because we kind of throw that phrase around kind of blasé, and it's kind of an important thing. I want to make sure everybody understands why that is. So I'll put it in the form of a slide here in a second. So 8-bit register. Why is 255 the max unsigned value that can be stored? Somebody who hasn't answered yet today. So you said this multiple times, right? We can say something very similar, and for a 16-bit register, why is 65,535 the largest unsigned value that can be stored in a 16-bit register? Go ahead.
Because that's the decimal equivalent value for 8 places of binary digits, assuming all have their max value of 1.
Okay, so in an 8-bit register, I have 8 spots, 8 buckets, right? So my largest unsigned 8-bit number is 1, 2, 3, 4, 5, 6, 7, 8. That guy. All right, and if I convert that binary number into decimal, I will get the value 255. Ones place, twos place, fours place, 8s, 16s, 32, 64s, 128. So this is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. That makes sense? Similarly, if I was dealing with a 16-bit register, you have 16 ones in a row. That the decimal version of that is 65,535 for an unsigned value. What's the largest signed value that will fit in 8 bits? Go ahead. It's 127. So this is unsigned. And signed, this is 127 signed. I'm not going to really talk about why yet. We're going to look at 2's complement here within the next couple of weeks or so. But, this value is actually encoded right now as a 2's complement value. So the largest signed value that will fit in an 8-bit register is 127. The smallest is negative 128. And that'll make sense once we look at ways of representing signed numbers. Because we have like the easy way that has some problems, and then we have the 2's complement way, which isn't necessarily hard, but is an optimization of the easy way that doesn't have the same problem as it. That's your foreshadowing, I guess. All right, so when we talk about 8-bit somethings or 16-bit somethings or 32-bit somethings, and we start thinking about the maximum values in it, I'm not asking you to memorize 255. This is 2 to the 8th power, right? 255 is 2 to the 8th power. 112. If we were dealing with a 16-bit register, it would be 2 to the 16th power. 32 would be 2 to the 32nd power, so on and so forth. All right, that's where those values are coming from, based on the number of bits. Okay, so it's an important thing for us to know when we're talking about computer architecture, because if our destination register is 8 bits or 16 bits, and we put something in there that won't fit, it's going to smush the bits that it can fit in, and then you're going to have leftover bits that go somewhere or nowhere. That's where these flags come into play, where we can then check the flags after arithmetic and say, is there something I should know about? Make some sense? Okay. Okay, so then we started looking at these load instructions for loading stuff into a register. So this is loading an unsigned value. And since it's a double word, these are 32-bit registers then. Did it say that somewhere, that these registers are 32 bits? Well, here, let me put that in a slide here. We'll just call it sizes. So we've heard of a byte, right? A byte is 8 bits. Then we have something called a word. A word is 2 bytes or 16 bits. Then we have a double word, which is 2 words or 4 bytes or 32 bits. Does anybody know what the thing that's one size smaller than a byte is? Nibble. A nibble. And this is a 4-bit value. Half a byte is a nibble. Go ahead.
Isn't word size dependent on the specific architecture?
It is. But modern architectures typically will treat a word as 2 bytes, which is 16 bits. But the historical thought of it, that's absolutely true. They would have had to define what a word is. And frankly, I'm making an assumption that ARM treats a word as 16 bits. I think it does. I'd be surprised if it doesn't. But yeah. So a double word would be a 32-bit register, which makes pretty good sense. That sounds like a nice size for a register, something that they would probably go with. Although I would be surprised if some of these registers in the most modern ARM architectures aren't flagged as different sizes. I would guess that some of these are treated as 8 bits, some of them are treated as 16 bits and 32, and there's probably 64 and even 128 registers as well. Okay, so kind of going back down here. So loading a double word from memory into a register. So a double word has an implied size of 32 bits based on what I just said, and I'm going to call it 98% certain that's going to be the size. But whatever a double word ends up being in this architecture, that's what it's loading from memory. Where can it find that word? What's this? Somebody else who hasn't answered today. What's that syntax right there representing? We'll eventually run out of people. So as soon as you know one, you should probably answer. That way, the harder ones, the next one could be harder.
It's like load in register 1. What's in register 2 plus 40?
Okay, tell me more about that. The part of it that I have highlighted there, you kind of glossed over pretty quick there. So what do you mean? What's in register X2 plus 40?
Like, so let's say you have like 500 or something in there. Like it'll add 40 to 500, so it'll be 540, and you put that into register 1, and the 500 will stay there.
Okay, yeah, that's not how it works.
Okay.
It's not horrifically off. It's not horrifically off. You just haven't applied it to the reality under the hood. Go ahead.
Is that an array?
It is pretty related to an array. Don't let the square brackets fool you. So yeah, it is very similar to an array. So based on that, you want to take a stab at it? No. So didn't you already answer today?
I did, yeah.
Yeah, it doesn't count. I'll only come back to those who have answered out of desperation. Because it occurs to me that when you have 2 or 3 people who always answer, those are the 2 or 3 people who actually know what's going on. And then everybody else, when I say, does that make sense? And they nod and smile, it doesn't make sense. They don't know what's going on. We talked about this last class, right? Didn't I threaten a quiz last class too? And I threatened a quiz yesterday. You didn't even know about it. I threatened Maddie with a quiz yesterday. So this should have been something we studied. This could have been the quiz. Go ahead.
Is this the Algebra thing?
The who? The who?
The LGUR thing?
Yeah, that's the thing we're
We
talking.
started talking about it, but
We talked about this part of it.
Array, contiguous memory, so that X2 40 position and load that to X1.
Okay, so if this guy is representative of an array, arrays live in memory and contiguous memory. What does contiguous mean? All in a row. Contiguous means everything's in a row. So we're saying go to base address that's contained in X2. Whatever X2 holds, it says go to that place in memory. Now, take 40 memory size steps forward. Okay, so we'll take 40 probably byte size steps forward, and that's going to leave us sitting at a certain byte value. And whatever value lives at that byte, that's the guy we want. So we want, this is effectively bucket 40 of an array that begins at whatever's in X2, and memory address represented by X2. Make sense? This is how arrays work. This isn't something new. If we go back to, I have it in this guy here. So if we think about arrays, we're using Java or something like that, and I say I want an int array, AR is equal to a new int array of size 5, something like that. You know, the value that's in AR is going to be some memory address, right? If I were to print out AR is going to equal some memory address that is the base address of the array. So then when we go and say AR at bucket 0, this is like saying AR plus 0 times size of int, where in Java an int is 32 bits. So 0 times 32, or in terms of bytes, it's 4 bytes. So this is, we'll just use for an example here. Let's just say our memory address is 100 in this example. So this is 100 plus 0 times 4 for 32 bits. 4 times 8, so this is 4 bytes or 32 bits. So 100 plus 0 is 100. That means bucket 0 of my array lives at the same place as the base address of the array. If I want bucket 1, 1 times 4 is 4. 100 plus 4 is 104. AR at bucket 1 lives at an offset of 1 from the base address of AR. This is how arrays have always worked. Okay? So because of that, here, I'll just make a second. So we'll say AR bucket 3. This is 3 times that. This is 3 times this. So this equals 112 for that memory address, and this equals 100 for that memory address. So the way arrays work and the reason that they're stored in contiguous memory is they are based off of the base address where the array starts, that's its base address, where it begins in memory, and then taking an offset from there, taking steps, so many steps from there to get to a value that lives somewhere in that array. Make sense? Okay. And we kind of see here that the syntax for ARM assembly is influenced by that kind of array syntax that we're used to from C, C++, Java, C#, the square bracket-y stuff, right? Okay, so this is saying I'm going to load into this register a value from memory. Okay? As opposed to storing. So these are the opposite sides of the same operation. So I load into a register. I store into memory. So let's put that on a slide here. Load versus store. We load into a register from, actually, we're going to say we load into a register. So let me just peek real quick. I'm pretty sure they have some load instructions that will load direct values. No, they don't. So all the loads are from memory. I thought we might be able to load an immediate. We can't. So we load into a register from a memory location. We store into memory from a register. Let me make sure that's true as well. We can't store immediates. Yep, looks like it. All right, so load versus store. We load into registers from memory. We store into memory from a register. Make sense? Which kind of makes sense. I mean, the load maybe is a little bit cryptic, but the store, we store things in memory. That part makes some pretty good sense. So the load must be the other one. Okay? Okay, so we load or we store. So store unsigned is we're going to store into this memory location, which actually changes. This is kind of a little bit different syntax than we've been used to because the destination is actually the second parameter. Up to this point, the destination has always been the far left parameter. Actually wonder why they did that. It's probably some performance thing with this offset syntax here is my guess. All right, so we're going to store into this memory location. What memory location? Whatever the base address stored in X2 is, plus an offset of 40 bytes. We're going to store at that place the value that's currently contained in X1. Make sense? So this is this doesn't remove the value from the register. This just copies whatever's currently in the register into, we're storing it long-term in memory. That way we can potentially go back and now use that register for something else as long as we've remembered where we just put that thing. Okay, so by definition, these are unsigned with the little u in there. Actually, so that's actually kind of weird. So this u doesn't seem to stand for unsigned because unsigned seems to be the default because this is a signed word with an S. The R, I'm sure, stands for register. I don't know what the U stands for. Good question. It doesn't necessarily matter. It's more interesting. Okay, so load signed word. So very similar instruction. We're loading into a register. So we're going to load into X1 the value at this memory address. Now, why do we need to have two different instructions? One for loading a value as is versus loading a value as a signed value. Anyone's allowed to answer this one. Why do we need two instructions for that? Go ahead.
Because certain values, look the same in binary. So they would be able to say, I want this as a signed versus I want this as an unsigned. This is kind of necessary.
Okay. I said it last class, and I said it a few minutes ago, but it was one of those statements I made that was, almost like in passing, right? I said that signed values are kind of encoded. I've mentioned 2's complement. And we're going to look at the specific way they're encoded. But the point is if you have an 8-bit number, in order to treat that as a negative number, you have to know that it was encoded using 2's complement. Somebody had to let you know that that was the case. Does that make sense? So otherwise, you could just read that 8-bit number as whatever the unsigned value would be. No problem. You just convert it to decimal. We all know how to do that. Converting to decimal. Let's just throw that on the slide real quick. So if I have a value, let's see, binary to decimal. So if I have something like 1 0 1 1 0 1 1 1, something like that, and we want to convert that to decimal. This 1 right here is in the 1's place, 2's place, 4's, 8's, 16's, 32's, 64's, 128. So this is 128 times 1 plus 64 times 0 plus 32 times 1 plus 16 times 1 plus 8 times 0 plus 4 times 1 plus 2 times 1 plus 1 times 1. You add all those up, that's 128 plus 32 is what, 160, 176, 180, 183. So that's 183. And you can use this the same pattern, whether we're dealing with a base 2 number or a base 8 number or whatever. The thing that would change is if we were a base 8 number, this is the 1's place, this is the 8's place, this is the 64's place. Okay, if you want to read this a different way, if this is base 2, this is the 2 to the 0th place, the 2 to the 1st place, the 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. If this is base 8, this is 8 to the 0th place, 8 to the 1st, 8 to the 2nd, 8 to the 3rd, 8 to the 4th, 5th, 6th, 7th. Make sense? So that's what those places are. We multiply that place times the value that's at that place. Add it all up, and that gives us the decimal equivalent of that value. So if we're going from a base to decimal, it looks like this. Okay. Go back here. So if we're saying we want to load a value from this place in memory into this register, and we specify that the value we're loading is actually a signed value, then we're flagging it as the value that we're putting in X1 is not using all of the bits for magnitude. It's using one of those bits for sign, but it's not just using the bit plain Jane for sign. It's encoded in whatever the way negative numbers are encoded in this architecture is, which today that's going to be 2's complement, which we'll talk about. But I'll just keep saying it for now. But 2's complement is an encoding of a negative number in a binary value. Okay? But we do need to specify that it is signed. That way it's treated as such moving forward. When we go to use this value from X1, there's a big difference between what its value might be if it's treated as signed versus what its value might be if it's treated as unsigned. Because if it's treated as signed, we have to decode it. Well, we have to potentially decode it if it's a negative number. And there's an easy way to tell whether it's a positive or negative number at a glance. But if it's a negative number and that thing is flagged as being a signed bucket, we then need to decode it to get its actual value. If it's flagged as an unsigned bucket, we just go with it as being unsigned and we just convert it to its decimal value if we want to get its decimal equivalent. All right, so that's why we do need to have instructions specifically for working with signed versus unsigned. All right, so store a word from a register into memory. So this allows us to deal with half the default size. So instead of working with double words like we are up here, which I've advertised as 32 bits, feel fairly confident in that. But if we generically call them words versus double words versus bytes versus nibbles, we're fine. So we have the normal store into a register. We'll store a double word, so 32 bits into that register, whereas store word will store into a register the value that lives inside of this memory location, but as a word. So assuming that these registers are 32-bit registers, if I'm only storing a word, which is going to be 16 bits, I actually only need to use half the register to store a 16-bit value, right? So potentially, if we have two words that we want to store, two 16-bit values, we can fit those into a single register. Does that kind of make sense? In terms of memory space, we could fit them into a single register. In Intel-based assembly, we could, if we talk about one of the default 16-bit registers, there was a register called AX. And one thing we could do is we can get the high and low portion of AX. So we can say AH versus AL. AH was the first 8 bits, AL was the second 8 bits of AX, if you wanted to deal with it in halvesies. Okay. I suspect there's going to be a similar type of situation here. Although, as this stands right here, if I'm storing into this register X1, this 8-bit value, the 16-bit value, since we're storing a word, I would presume that what's going to get stored inside of, I'm sorry, not store, load. Is there a load? Is there a load word? It's a load signed word. Yeah, so like this guy right here, load signed word. A word is going to be 16 bits, half of the default size of a double word. Okay, so this is going to be 16 bits. We're storing into X1, which can hold a double word. We're storing only a single word. I would presume what would happen is the first 16 bits would be all zeros, and then after that would be the actual value you're grabbing from memory here. Does that make sense? Now, where that could become important is if you store a value that is, let's say that what you grab from here well, it's only going to take it. Since we're dealing with memory here, here's our base address x2, here's our offset of 40. There's going to be a value that's there. When we go to grab that value, we have to decide how big of a, I guess pun intended, how big of a bite we're going to take in order to grab that value. If we know that value is of a size word, we're going to take a 16 or we're going to take a 2-byte size byte. So how do I say it instead of saying the word byte? We're only going to grab the next 2 bytes if I'm taking a word. If I'm taking a double word, I'm going to grab the next 4 bytes to get a double word. Okay? So the fact that I'm choosing to load a signed word here, that says that when I go to this base address, then jump forward an offset of 40. At that point, I'm at the beginning of the value that I want. I'm going to either grab the next 2 bytes. In this case, since it's a word, I will only grab the next 2 bytes to get my value. But if I was not loading a word, instead I was loading the default, which is a double word, I would grab the next 4 bytes to get the whole value. Does that make sense? So having a different instruction for grabbing a word versus a double word also is important because that tells you how you're going to traverse memory. Okay. It doesn't really tell you how to traverse memory. It tells you once you get to your place in memory how big of a value you will get. And that further, I think I mentioned last class and I said again today, that I'm presuming this is number of bytes you walk forward. I think this kind of solidifies that as probably being true. Because if I go to my base address x2 and I walk forward 40 bytes, this gets me at a new address. And then since I'm grabbing a word, I'm going to grab the next 2 bytes from that address. And that'll be my value. Versus if I'm just doing a normal load, I would grab the next 4 bytes from it. So that says we're going to have a consistent gate of 1 byte per step as we walk through there. So this plus 40 is always treated as bytes. And then what we grab once we're at our memory location, we walk through memory, we're standing there, we look up, and then we say, okay, well, I'm going to start with this guy, but how far forward do I do to get my actual value? And that depends on whether I'm grabbing a word, a double word. Load half is going to be a half a word, which is a byte. It's kind of interesting. Well, they wouldn't just call it load byte. Whatever. Okay, so that makes some sense. This whole offset stuff. All right, so load a signed word. This is how we can work with signed values from a practical perspective. We'll look at how signed values are actually stored soon. Storing a word, again, when we store, we're storing into memory. So that means that we're going to go to a place in memory where started offset wherever x2 points to, walk 40 bytes forward. That's the location where I'm going to start storing my value. I'm going to presume that the value in x1, I only care about the more than likely the low half of that guy because I'm only storing a word. So I'm storing half of the capacity of x1. So I'll grab the last 16 bits of x1 and store it at this location right here. So it'll actually live at memory location based on what 42 is, or based on what x2 is. Let's say x2 is 100. This will go to 140, and then we'll store it at 140 and at 141. Those 2 bytes to give us our 16-bit value. our word size value. Those are the two buckets we'll take up. Let me explain that. There's some blank stares here. Okay. Store in memory. Let's draw my pictures. Not close enough. Okay, so we're going to say that this is our memory for right now. And then I'll go ahead and, using our example here, we'll say that x2 is memory address 100. That's what that guy holds. And then we're just going to assume these are our memory addresses. So that's memory address 100. Okay. So if we have a value, I'm going to have to use something smaller than 40 because I don't have 40 steps to work with here. So we're going to take steps of 4. Okay, so if I say something like x2 comma 4, what this is saying is it's saying go to the base address x2. So x2 is 100. So go to memory address 100, then take 4 bytes in. 1, 2, 3, 4. Okay, so these are bytes, bite-sized steps. All right, so now I'm sitting here. Now the reality is between here and we're going to say the smallest value we can store is a byte in this example. Okay, so I started here, 1 step, 2 step, 3 step, 4 steps. So I'm at this address right here. So that means the first byte that I could read is the value that lives right here. So let's say this was a 7, but that's a byte. Now, if I was loading a word from there, let's say this was holding a 72. Now, it's actually going to hold the binary version of those guys. Okay, but for right now, we're going to store in a decimal. It's easier for us, right? So I'm at this memory location, and I'm trying to grab a word. The word I would grab is the numeric equivalent 72. 16 bits worth of values. As opposed to if I came here and I was trying to grab a double word, the default, I would grab the next 4 bytes, 7218. So I would be getting the value 7,218 from that. Okay, so just because I've come to a certain place in memory, how big of a value I grab next is going to depend on what I asked for. Similarly, the next thing was to grab a half, right? So load and store half. So half is 1 byte, half of a word. Go ahead.
I think half might be 8, like a double word might be 64.
Half might be what?
You got load byte there.
Oh, do I? Okay, so load byte would definitely be 8. Load half then would be 16. A word would be 32. So a double word would be 64. Yeah, that could make sense. Otherwise, half and byte would be equivalent. I can go with that. Doesn't necessarily matter. It's the word size we'd have to have. And this kind of goes back to what Josh says, is the architecture would tell us how big these things are. But it sounds like what you're saying is right. He's saying, if we just create a slide for what these things mean in ARM based on evidence. Let's call this ARM sizes. So a byte is 8 bits. So that's a constant, right? That's not an ARM thing. That's what a byte means. Okay. Then a half, which is a half word. So I'll put it in parentheses here. Word is going to be 16 bits. So that's like our Java short for the short primitive type. And then a word would be 32 bits. That's like an int. And then a double word would be like a long, which is 64 bits. Make some sense? I think those sound like fair values. Oh. Oh, I put that way up there, didn't I? Where am I putting this? Oh. Yeah, I like just throwing slides randomly throughout the presentation. Just put them all sorts of places. It's good. Very easy to follow. Okay, so given that, if I am loading or storing a byte, if I came to this memory address right here and I was grabbing a byte, I'd grab the 7. If I was grabbing a half, I'd grab the 7 and the 2. If I was grabbing a word, I would grab the 7, the 2, the 1, and the 8. If I was grabbing a double word, killing me. All right. If I was grabbing a double word from this base offset, I would grab all of these, the next bytes. Does that make sense? So when we do an offset, that math is always the same. Start at a base address and take so many bytes in to get us to our base starting point. From there, what we are grabbing will depend on what we ask for. Are we grabbing a byte? Are we grabbing a half? Are we grabbing a word? Are we grabbing a double word? Make sense? Okay, so that's why we have all those different ways of doing things. And if you really think about it, this is kind of connecting to our programming languages. In general, we talked about this some last class, but in general, memory isn't such a huge issue anymore for us, right? Most of the time, we would be fine storing everything as 32 or 64-bit values. Probably. Most of the time, for most applications, because we have tons and tons of memory. We talked about embedded systems a little bit last time, where we had to play by a different set of rules because now there's new limitations. But in general, who cares? But remember, these instructions, these ARM instructions, even though we're going to write them by hand, obviously we're going to be solving fairly simple problems, right? Otherwise, you would have thousands of instructions you'd have to write to solve. Like let's say you had to write merge sort or something like that in assembler. It's not an impossible program to write, but it would be way more complex than writing that in Java or C# or something like that. Because we're relying on that Java or C#. Well, if you write merge sort in Java and target the, actually Java is probably the bad example. If you write merge sort in C++, and you compile it for ARM, it's that compiler that's going to give us those ARM instructions, right? So one reason why ARM has to have the ability to deal with bytes and the equivalent of shorts and the equivalent of ints and the equivalent of longs is because the source language, C++, supports those. Does that make sense? So if you're going to store a long in a C++ program, you're going to need a double word to hold that long. So the the instruction set itself has to be compatible with a language that can compile to it. Now, let's assume you had a language where longs don't exist. Or, actually, this is actually a realistic example. For instance, in C++, there's actually an even bigger primitive type than long, called a long. So a long is 128 bits, so double the precision of a long, or double the magnitude of a long. Based on what we've seen so far, does ARM have the ability to handle that? We haven't seen it yet. You could bridge it, right? You could kind of use two things, but at the surface, we haven't seen a load or a store that directly handles it. It could be because we're looking at the leg instead of ARM, right? We're not looking at the full architecture here. We're just looking at a kind of a cut down version. But presuming that it doesn't support the ability to store single value that's 128 bits, that compiler is going to have to take it into consideration. And when it compiles stuff, it's going to have to treat it as a long and hope that's a big enough value. Because fairly often, when we use primitive types, we use an int even though we're only going to store the values 1 through 10. So there are some constraints, there are some limitations that we might have to deal with that are related to either the compiler itself or the underlying architecture that we're targeting that might change how we solve our problem with the high-level language because of the capabilities of the underlying low-level language. Kind of make some sense? There's all sorts of these things need to be compatible with each other for us to pull it off. Most of the time, we don't need to think about that. Most of the time, if our compiler supports compiling down to a certain architecture, chances are you can write the high-level code the way you want, which would kind of indicate that I'm pretty positive you can write C++. In fact, I've done it. You can write C++ code and compile it to ARM. Therefore, it's pretty likely ARM has the ability to store a quad word. It's 128 bits because C++ supports long. Okay, but the other alternative is the compiler could give you an error. I don't remember the last time I used a long in code, but they exist. It's possible the compiler could turn around and say, since you've targeted ARM as your architecture, that primitive type is off limits. Change your code to not have to use it. That makes sense? So those are things you might have to do. Okay. So load half, store half, blah, blah, blah. So we understand the difference between loads and stores, load byte, store byte. Okay, so load exclusive register. This is a load. So we're loading into a register and we're loading the first half of an atomic swap. All right, so this is saying go to base address x2. Give me the value that lives there, which is we've been operating as if it's a byte. And we're loading the first half of that guy. So earlier I mentioned that with our registers in like Intel, we can have a high and a low portion of the register. So AH and AL. So does this let me get, this is the second half. Is there a load? So it looks like based on this one, what we're looking at here, we can't directly access the second half of the register. We can grab the first 32 bits since our registers are 64-bit based on what we've figured out today. So if our register is 64 bits, we can get the first half of it, which is 32 bits, and store it, store our value in those first 32 bits, abandoning the second 32 bits, With that in mind, though, we probably would not be able to rely on the second 32 bits all being zeros. So if you loaded only half the register, you'd have to then use only half the register. So I think I'd have to see an example of when they'd want to use this. This might be one of those things that they only grabbed half of the instruction suite of this from ARM for their leg V8 thing. So you really can't do the first and second half, but my guess is ARM supports both first and second half. Okay, so we're loading into a register, we're storing in memory. See, this guy says store second half of an atomic swap.
Those two might work.
So it's talking about swapping. So is this taking something out of memory, storing it in X1? Okay. It does seem to work together, but we still don't have a way of getting that value into the second half of X1. So I think the ultimate goal here is to take something that was in memory and something that is a register and ultimately do this. Swap those two. So, and it's calling an atomic swap. What does an atomic instruction mean? This is a 450 thing, right? A couple of you have had 450. Several of you have had 450. What does atomic mean?
Can't be interrupted.
Okay, so something that happens as if it's a single move. Okay, so that atomic swap, when I take this guy to this guy, and so this is the first half of an atomic swap. Okay, I don't think they're talking about the half of the register. I think they're talking about the first half of the swap, right? So they're saying we're going to take this. So we're loading into a register. So I'm at this guy here. We're going to load. So this is X1 here. We're going to load into X1 this value. And that's happening atomically. Then we're going to store into that place in memory what used to be in X1, but now I've loaded that into X1. How does the swap actually occur? X1 is going to equal the memory at bucket X2. And then the memory at bucket X2 is going to equal so at the very least right here, they're not showing us the direct swap. These would overwrite each other. So if we switch this X1 to like X5 or something like that, we can load into X1 memory address from X2. Then we can load into that memory address from like X5 doing the swap in memory. And it's guaranteeing these guys are atomic. And then what's the X3 here for? A 0 or 1, probably a true or false, whether or not it worked, it happened. We'll have to wait to see an example of this being used. But the atomic aspect of this says happens as if it's uninterrupted, happens as if it's one CPU cycle, something along those lines. And we can kind of think about the big picture here that if you have a value in memory and a value in a register and your ultimate goal is to swap those two guys, having that happen atomically might be a good thing. So there's a data path that allows that to happen, but we're not seeing the full picture here of how that might actually occur. Makes sense that might be kind of a feature of the processor that allows swapping to happen atomically. Okay. All right, so here's like a move wide with zeros. So we are loading a 16-bit constant. So for instance, like 20. So we're saying treat this as a 16-bit value. So whatever it does not take 16 bits to store the value 20. Right? If we have the value 20, how many bits does a 20 take to store? So this is our other pattern for conversion, right? Convert 20 to binary. So how do I convert the decimal number 20 to binary? What's the pattern for converting any decimal number into any base? In this case, divided by 2, because I'm converting it to base 2. So 20 divided by 2 is 10. 10 times 2 is 20 with a remainder of 0. So we'll record the remainder. 10 divided by 2 is 5. 5 times 2 is 10. Sorry. 5 times 2 is 10 with a remainder of 0. 5 divided by 2. 2 goes into 5 2 times. 2 times 2 is 4 with a remainder of 1. Not close enough. 2 divided by 2. 2 goes into 2 one time. 1 times 2 is 2 with a remainder of 0. One divided by 2. 2 goes into 1 0 times. 0 times 2 is 0 with a remainder of 1. Then we read our result from the bottom up. So that is 1 0 1 0 0. So it only actually takes 5 bits to store a 20. But we're storing it as a 16-bit value. So, well, we're grabbing it as a 16-bit value. So the 16-bit version of a 20 is those 5 bytes plus another 11 zeros. But those make sure those zeros come in the front, not at the end, because the end will make this value a lot bigger value, right? And so now this is 2 to the 0. This is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place. This is the 32s, the 64s, the 128s, 256, 512, 1024, 2048, 4096, 16, 536. All right, whatever. But in any case, these are all zeros. So 0 times that plus 0 times that plus 0 times that doesn't have an impact on the actual final value. So this will take that immediate value as a 16-bit value. So this guy right here as a 16-bit value. So it loads that 16-bit constant into our register X1, but our register X1 can actually hold 32 bits. So now what's actually going to be inside of X1 is that. The first 16 bits of which is a bunch of zeros, followed by the 16-bit representation of that value we just stored, which only took 5 bits, but we have 16 bits to work with, so it's padded out to 16 bits. Make sense? Okay. Okay, move wide and keep. This actually could be an interesting game to do the high and low part of a register. So this is saying we're going to load that same 16-bit value, like a 20, into X1. So this is going to load into X1. This would be the low half of X1. It would load in that 16-bit representation of 20. But it'll leave the high part of X1 unchanged. It won't pad it out with zeros. So if you needed to store to get something into the high part of a register and the low part of a register, we can, let's say you had, I'll give you a real example of this. Okay, so if I want to load this guy into AX, really it's actually 16 bits total, right? $32 bits total, rather. That's the 32-bit representation of a 20. But let's say I want to get that guy loaded into, I happen to know it's only a 16-bit value. It's actually less than a 16-bit value, but I happen to know that this guy's 16 bits of this guy is padded. And I want to get him into the high half of AX, the first part of AX. What I can do is I can left shift this guy 16 times, which would do this with it. They'll do that with it. So we've multiplied this by 2 to the 16th power. So now it's a much, much, much bigger value in terms of its actual magnitude. But if I store that value inside the 32-bit register, the first 16 bits is actually my representation of my 20. And then using this other, they haven't showed us the shift things yet, but I'm assuming it's somewhere in that list probably, or it exists at the very least. Then we can instead do a move wide with keep, which says I'm going to load into the low half, maybe the value 15, but I'm not going to change the high half. So now you have the high half, the first 16 bits being the value we just stored that we left shifted 16 times. And then the low half being the value we just moved in there that was only a 16-bit value. So now we have one register that's holding two 16-bit values for us. Getting those out might be fun. Okay, but I'm sure in the full architecture, our full instruction set, there's things for grabbing the, probably grabbing the low and with zeros, padding with zeros, then grabbing the rest and right shift 16 to give you the value that was there, to undo it. There's ways at getting at those things. All right, just kind of speculating. Don't worry about shifts yet. It'll come in. I'm just kind of, was thinking how you might get at the high and the low part of those registers using what's called a bitwise shift. Now, several of you have been in classes before where we've talked about bitwise shifts, right? And because you can do this and it'll come up in this course again too, but you can do this in languages like Java and C++ and C. If you could also do bitwise ands and ors. But for instance, if you do 5 left shift 3 like that, what this will do, actually let's do 20 left shift 3 because we already have the binary value for 20. This is going to be, what is it, 10100. So to left shift that guy 3, it'll be 123. So you've actually multiplied 20 by 2 to the third power to left shift it by 3. So this guy will give you a value that is 20 times 2 to the third power. That'll be the resulting value, in case that's ever handy if you're doing base 2 math stuff. So it's a thing. But that's what this shift is, the shift stuff is for. So there is a mathematical consequence to it. But if you're using it relative to registers, you might be using it to position bits in the right place within a register, knowing that when you take it out, you're going to undo your shifts. So you're not worrying about the impact you had on the magnitude of the value. You're just worried about, like, oh, I need these to be the left 16, so I padded it. Then I need to, when I pull it out, I'm going to unpad it to get it back to where it was. Something like that. Okay, then we have our typical logical operators, ands, ors, all these guys. So what does an and do? This goes back to our original kind of pattern. So we're going to store inside of x1. So our destination is that first parameter. We're going to store in there x2 anded with x3. Okay, now these are bitwise ands. So if we're in a language like Java or C++, these are bitwise operations. So these are operations which operate on individual bits of a value. So for example, left and right shifts add or remove zeros from the right of a binary representation of a number. And then we have bitwise and anybody know what the operator for bitwise and is in like a language like Java, a C-based language? Single ampersand. So you're used to making Boolean expressions in Java using double ampersand, right? This is an and in Java. That's a normal and. Requires both sides of it to be Boolean expressions. A single and is the bitwise operator. That's expecting you to have two numbers. And it's going to say, I'm going to take those numbers, I'm going to look at them in their binary equivalents. And I'm going to and those guys together in a bitwise format. Let me show you what that means. So I'll just put this, I'll say it like this. In Java or C or C++, it came from C. All right, so if you're doing a bitwise and, let's say we had a 1, 0, 1, 1, 1, and then we had a 1, 1, 0, 1, 0, and we want to bitwise and these guys together. What we're going to do is we deal with it on a individual bit basis. So for an and to be true, both sides need to be true. So 1 and 1 is 1. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. See how that works? All right, so that's a bitwise and. If we're doing the same thing as a bitwise or, I'll just do it in place here. 1 or 1 is 1. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. 1 or 0 is 1. Makes sense? Then the last one is an exclusive or. What's the difference between an or and an exclusive or? Good.
An exclusive or is one or the other, but not both.
A who?
One or,
Oh, one or the other, but not both. Yep. Okay, so if we were doing this as an exclusive or an XOR, 1 XOR 1, or some people pronounce it 1 XOR 1. I never did, but I've kind of started doing it over the years as I've heard some students call it that. What have you heard it pronounced XOR? Maybe?
I don't know if I'll switch between XOR and XOR.
Well, that might be what you do. I'm saying, have you heard other people? And I've heard myself say XOR, but for other reasons. All right, so we have 1 XOR 1 is actually a 0 because it's one or the other, but not both. In this case, we have both. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. 1 XOR 0 is 1. So that's the bitwise XOR or XOR. Actually, XOR is kind of hard to say when you're doing it fast like that. It's like a tongue twister. All right. So questions about bitwise operations, ands, ors, blah, 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 blah stuff. Yeah, so this inclusive or, which is a standard or. Yeah, see, they're showing you the, and this is Java. So exclusive or in Java and C and C++ is the caret. Okay. Not to be confused with, many of you may have run into this when you first started doing some programming stuff. You you thought, oh, I need to take something to a power. And it's like 2 to the 4th power. You said 2 caret 4 because you think that's what it should look like, right? And you got some weird number that definitely wasn't 2 to the 4th power. Because what did it do? It took 2, the binary version of 2. It took the binary version of 4 and it exclusive OR'd those together, giving you a new value. Does that make sense? And they're like, this math doesn't work. Java's broken. All right, so in Java, what do we use? Math.pal to take something to a power or just write your own function? You know, why use built-in stuff? Just write your own. It's more fun. All right, so in any case, this is the exclusive OR in our C-based languages. This is the, exclusive OR in C-based languages. Exclusive bitwise OR in C-based languages, exclusive or normal OR, normal bitwise OR in C-based languages, normal bitwise AND in C-based languages. Okay. Similarly, you can do those things relative to immediates. So that is store inside of a certain register the result of bitwise ANDing another register with an immediate value. Same thing, just working with immediates instead of something else. Here's our shifts. Left shift, right shift. Those things we just talked about. Even here's the symbols for it. Okay, so what did I have you read to for 2.2? I think I'm actually going to still keep you here. So don't read any more. Study everything we talked about. We will have a quiz on Tuesday related to this chart, arithmetic, data transfer, and logical stuff, not including the shifts. I want to talk about the shifts some more, but anything from this line here and up in this chart is fair game for the quiz on Tuesday. Make sense? All right. I will see everybody on Tuesday.